I've been accepted anyway, so I figured that's fine. Right. Yeah.
Good morning, everybody.
Good morning. Oh, dang. It's Thursday. I have 50 tonight. Yeah. Are you excited? I'm excited. First night. Yep. Yeah, I'm so excited. Yeah, I know. Also, that Ashland tournament that we usually go to is going to be in November this year. So I'm hoping that we can get like a group that like hit. But before we say like yes, yeah, we can get like a group that actually is big enough to go. In November, yeah. I can't remember. I'll have to look and let you guys know because Haley was like, I'm busy in November a lot, so I was like, oh no. Yeah, it's not over next week, I know that. So then it's like the weekend. I think it's like the weekend before that, maybe. Which is probably going to be busy. I did not Saturday night this morning. Yeah, my boyfriend left. I went to bed last night and I was like, hey, now I don't want to take a shower. Developed into like a full-on, like, this is a home, but right. It's like, well, has the potential. Yeah. So I was like, all the time. The problem that most likely happen. So, it's like, if I could manage, this is happy.
Hi, Debbie. How you doing? Good.
We're talking about the paper thing. I forgot because yesterday was the day that I was taking my friend.
Good morning, Shelby.
Oh, really? Yeah. And so I was like, I didn't think I needed an admission ticket because they said it like 6:30 in the morning. Yeah. I didn't think I needed this. Yeah, I didn't bring one the first time. I was like,
Shelby, are you on one of the sports teams? Are you on one of the sports teams?
Yeah. I was like, I literally.
Which one?
I'm ready cross country. But my
great.
was like flip-flopped. I was like, you gotta be kidding. You gotta be kidding. And then also, one of my essays was the exact same prompt. And I was like, I'm literally writing the same essay. That's really funny. Yeah.
Shelby, what's a good time for running 3 miles? It's a reasonably good time for running 3 miles.
Just on like an average day?
Yeah, just on an average day. And it doesn't necessarily mean for you. I mean, just for like, what would a typical person your age, let's say a woman in your age group, right, who is a runner, right? What might she run?
And it really depends on so it's like a big between your, like, is your real one quantitative or quantitative? No, they're pretty close together.
22 is a pretty good time.
That's like really cool. I did that, so I know.
Okay, so 3 miles in 22 minutes.
Minus like.
I'm sorry. Okay. Uh-huh.
I really know.
Right. Okay. No, just we're trying to get a ballpark figure for what good times are for that distance, right? Gabby is here. Shelby is here. Hannah is here. Victoria. Karen. Please get to a computer that works. We're going to need one. We're going to need to be on Excel today. So any of the computers that works. Jake is here. Melanie is here. Glenn. Does everybody have one of these? Okay. You're welcome. Well, we have 8:30, so why don't we get started? Good morning, Psych Stats. Okay, welcome to Wednesday. Congratulations to all of you on your excellent essays. I really enjoyed listening to them. I mentioned the other day that I listened to them in addition to reading them, and then also you hopefully got feedback in your Slater boxes. I don't know if you've picked it up yet, but you provided a lot of feedback to each other, and then I also provided electronic feedback to you. So hopefully lots of feedback, and it was a great session on Friday, in addition to the great session that we had on Monday. I really appreciate what you had to say about that difficult article on facial identity. That was not an easy read, but you made your way on through. And then Hannah had a very nice presentation for us. So thank you, Hannah. What I'd like to do is begin to embark on our new topic, which is going to be correlation for this week. And to help make that connection, before we talk about linear correlation, I thought we might set the stage by just hearkening back to what we were doing in chi-square. Chi-square is kind of like a correlation. It's an associational test, but it isn't one that is linear. It's one that's based on qualitative information. And we did quite a bit of work on chi-square, even for our last computer quiz. But one of the things we didn't have time to do was a manual computation of the chi-square statistic. How many people remember in Psych 200 manually computing the chi-square statistic? People remember doing that manually, and you might have used a computer, you might have used Excel. How many people are not sure they remember manually computing a chi-square statistic? Okay, most of us don't. Most of us are in that boat. We don't recall having done that. Maybe you actually didn't manually compute that. So we're going to warm ourselves up a little bit with that, and then we'll get into linear correlation. So both types, chi-square and the R statistic, are correlational. They're about associations. One is using qualitative variables. Okay, so to help us with that, I hope you'll join me out in Excel. Can we go out to the S drive? I've put up there a new practice set. And the practice set is in a yellow folder called chi-square or something like it. I'll go there with you. And there are two flavors of chi-square. Does anyone want to call off what the two different kinds of chi-squares are? We can have a chi-square test of independence, okay? What else could we have? A chi-square test of goodness of fit, okay? So why don't we, actually the easier of those two is the goodness of fit. So why don't we start out with that one? So if you went out to the S drive and went to 370, the resources folder, there are some practice sets, and within the practice set there's a smaller yellow folder called chi-square problems, and if you click on that, you'll see all kinds of things, including the handout that we have for today, but also there are two Excel sheets there. One of them says chi-square good fit, and that one should look like this. Okay, and we can click on problem one, and if you get that far, maybe you can raise your hand so we can see where everyone is. Okay, Karen, we're still looking for that one? Are you still looking for that? Oh, okay, that's all right. And yours? Okay, that's very, yeah, so that happened to Vanessa on that station.
Right.
Okay. Okay, I wonder what that's all about. I wonder if it's a function of how somebody logged off of there the last time, you know, and then maybe you're actually logging into a switch user or something. I don't know. Okay, so we'll give you just a moment to get out there. And I apologize for the small print. You have the print there. Maybe I can zoom in a little bit. Let me go to View, and here's a zoom. Let me see if 200 is too big. Okay, maybe that will work. Okay, so as some of the computers are coming up, we'll just set the stage here a little bit. So this is the chi-square test for the goodness of fit. And this is when we're really looking at one variable. And maybe you can tell me a little bit more about how this works. We're looking at one variable. And how would the chi-square for goodness of fit work for one variable? What do we do with the chi-square test for goodness of fit on one variable? We've got one variable. Okay. What do we do with that one variable? What do we do in general with the chi-square? We compare a what to a what? Okay, thanks, Gary. We observe value to an expected value, right? Okay, so what we might say is that on a particular variable, we might have 2 levels, we might have 3 or 4 levels. We're going to see how the observed frequencies across those different levels compare to some kind of expected frequencies. And you might remember that we have different ways of generating expected frequencies. A very simple way is what we can informally call the even-Steven model. That is to say that we have equal probabilities across the different levels of our variable. So we might have, for example, a situation where we're thinking about the factors that are influencing how students choose their courses for a given semester, okay? And these are some of the factors that they might think about. Some people are very driven by time of day. Some people are just dying to get into 8:30 a.m. classes, right? That's their biggest goal in life is to get into 8:30 a.m. classes. Others prefer to have later afternoon classes. So maybe time of day is one factor that influences a student's decision. It might be the instructor. It might be that you've heard good or bad things about a particular instructor. It might be the topical interest. It might be the perceived ease. And I say this every time I run this particular example. I'm always impressed at the honesty of my own advisees when they tell me, can you suggest an easy class because I'm taking this one and I know those are hard. So what's a really easy class? I'm impressed by their honesty in saying that. So you can generate other reasons for selecting courses, but these might be 4 reasons for selecting courses. Okay? And what we might want to know is whether these are equally likely. You might have a different model where you wanted to know, is this one occupying 50% of the probability, and these remaining 3 occupying something like an equal distribution of the remaining 50% of the probability. But in any case, we can say that we're going to go with an even-Steven model today, and we'll see if these 4 are all equally likely. Okay? So let's see if now all the computers are up. How many people have that screen all the way up? Is it still coming up? Okay. Okay. All right. If you'll bear with us, I'll keep on announcing it, and I've got this thing being recorded. So, all right, we'll see how we do. Sorry about that, Sarah. Okay, why don't we first get some hypotheses going? Okay, and how do we typically signify the null hypothesis? Does anybody recall? What kind of an H is it? H sub 0? Okay, so HO is going to be our null hypothesis. There's an HO. We'll put in a colon. Okay, and I'll offer you what will be for our course our favorite prepositional phrase. Overall, though, for me, this is my 3rd favorite prepositional phrase, and it is the phrase "in the population." Okay, so we're going to do something of a test here, an inferential statistic. We're going to try to draw an inference about the denizen population of students and what's driving their decisions on course selection. But we have a sample, and our observed frequencies are up there. In the population, the 4 reasons for selecting courses are equally likely. We have these 4 here. Okay, so we'll go with the even-Steven model in the population. 4 reasons for selecting courses are equally likely. Okay. So we're testing an equal likelihood model here using Chi Square. And we're using Chi Square again because we have these qualitative variables. Here, actually, we have one qualitative variable that has 4 levels. Okay? So we'll let you type in something like that. Spelling doesn't count. But what I think is important about this is we start out within the population so that we know that we're testing, yes, a sample, but we're hoping to draw an inference about the population, and we're testing the equal likelihood model. Okay? In addition to having a null hypothesis, what other kind of hypothesis might we have? A null hypothesis and a alternate hypothesis? Does that sound familiar? Okay. So why don't we do this? We'll do Control-C, Control-V, okay, and we'll create an alternate hypothesis here. And if the null hypothesis is HO, what might the alternate hypothesis be? Not HO, but H1, okay? And it will be largely the same in the population. The 4 reasons for selecting courses are, and here we're going to use that obnoxious phrase or that obnoxious word, not. Okay, like when somebody's trying to negate something, they'll say something sarcastically, then they'll say not. So we're going to say are not equally likely, and I'll make not capitalized. So we have 2 hypotheses: the null hypothesis and the alternate hypothesis. Who's okay with all of that? So far, this should all look very familiar. You've done things like this before in Psych 200. What we didn't do in Psych 200 in most cases was remind ourselves about the formal Latin logic associated with testing the null hypothesis. Anybody want to recall for us what that stroke of logic was called? we're going to test the null hypothesis using the if P, then Q, not Q, therefore not P. What was that thingy called? Anybody remember? Yeah. Modus tollens. Modus tollens. Okay, so we're going to evaluate this null hypothesis and see whether we can retain it or whether we should be rejecting that null hypothesis. Okay, so now it's time to take out this formula. Hopefully everybody's got this one. And it's got two sides to it. Can we go to the side that says chi-square test for goodness of fit? It's the simpler of the two. Okay? And one of the things we have to do is generate some expected frequencies. So I'm going to drop down maybe a row beneath the observed frequencies. It can be one or two rows beneath. Okay? And I'm going to put in the expected frequencies. And you can tell I've been on this sheet before, even on the one that you have, because I've kind of graded out. I'm going to leave the empirically observed values nice and dark, and I've turned these a slightly lighter shade of gray. Okay? All right, and let's see if we can follow this formula to generate some kind of expected value, okay, for this particular cell. So in this cell, we're talking about time being the leading factor for driving their decision on how they're selecting courses. Okay? And what we want to do here is follow this formula for the expected value. Okay? So what we might say is, well, I'll let you tell me. Anybody want to help me out? How am I going to compute that expected value? Go ahead, yeah.
Add all the numbers on the equation.
Okay.
Divide by the number of variables.
Really good. Okay, why don't we come over here and get a simple total? Okay, so join me in doing total. Okay, and what is our command for getting a sum? Let's all yell it out. We get a sum by putting in equals sum. Okay, we'll put in a left paren, and Karen's right on it. We're just going to have Excel do the adding for us. We're going to add those. And I come to an 80, unless I've made a typo. How many people can confirm the 80? Okay. All right, looks like we're doing well on that. Okay, so 80 is our total number. So if we have an even-Steven model and we have 4 categories and we have a total of 80 observed cases, what would our expected value be for the time condition? 20, okay, right? Did everybody see where that came from? Okay, so maybe it's not, how many people are not sure where that came from? It's all right for, okay? We can say this is going to be equal to the total divided by the number of cases that we have, okay? Which is going to be 4 cases, or 4 levels of this variable, and that's going to be 20, okay? Now the way I created that genotype was I said equals, I clicked on the 80, and I divided by 4 because I have 4 conditions. So far so good? Yeah, okay. Now I'm going to make an error that you might make during a computer quiz, but just to simulate that error, I'm going to say, okay, well, that's probably going to be true across the board, so why don't I drag this across the board? And I'll now drag it across the board, and what did I do wrong? Can you remind me? Here's what I did. I clicked on this, I said I want the 80, I divided by 4, that correctly gave me a 20. Then I dragged it across. What did I do wrong? Go ahead, Sarah.
You didn't freeze the total.
I didn't freeze the cell. Okay, right. So there's a couple of ways of doing this, and I don't remember if we've gone through the different ways of referring to the cell. I can just put in an 80. I can put an 80 divided by 4, and that's going to give me 20. And then I can pull that across. That would do the trick. Okay. I could also freeze the cell. Right, as we've done a few times, we can use the trick where I'll say, give me this one, and I'm going to go in and insert. Using this precision insertion, I'm going to insert a $sign to the left of the G. That freezes the G column, and also to the left of the 9, which is row 9. So I'm freezing the row and the column, and then I can drag that across. Okay, so a couple of ways to go there. Oops, excuse me. Divided by the 4 options that we have. Who's okay with all of that? Okay, so we have 2 ways there of referring to a cell. I don't remember if we did the 3rd way, okay? And there is a 3rd way of doing this. You can actually rename a cell to something that's helpful to you. So if you'll join me by clicking on the 80, okay? And there are a couple of ways of doing this, but if you're clicking on the 80, you might notice that in the upper left-hand corner, there's a G9. People okay with that? You see the G9 there? I think we can click into the G9. Can you, way up top, where's this G9? And can we put in a helpful reference for this, a helpful label for that? Why don't we call that thing the total, or just total? And I'll hit enter. Okay. And now anywhere I go, I can be anywhere in my cell, and I can say equals total. I think that's not a reserved word. and I get that number. Okay? I don't remember if we had done that before or not. So I can also say over here, I want this to be equal to the total divided by 4. Okay, and I can drag that across. And then if my total happens to change for this reason or the next, then everything just hot links to that. Okay? So it's pretty nice to build in that flexibility. Who's all right with that? Can you remind me, did we do that? I don't remember if we had named this. I know we had frozen the cell before. So you can use the literal value, you can use the freezing trick, or you can name it. Of those three, the one that I would recommend against is putting in the literal value 80. Because if it turns out that you just hard code an 80 there, and then later on you figure out that you or somebody else had made a data entry error, and they had the wrong number under instructor. They have 10, but it should be 11. You change 11, but you had hard coded the 80, right? So you'd want that 10 to become an 11. That turns that up to an 81. You'd want everything else to follow suit, right? And you'd have to go individually in and put in the 81 all the way around. So it's probably best to think about variables whenever you can do it. Okay? How many people have 4 expected values? Okay? All right, so now what we're going to do is something very similar to what we had done when we were computing standard deviations. Do you remember that we were in Excel and we had a list of scores? And then what was the column right next to that when we were trying to manually compute the standard deviation? Here are the scores. What was the next column over? The deviations. How are the deviations defined?
S minus M.
S minus M, score minus mean. Okay. Then we had a list of deviations. What did we do with our deviations? Next column over? Squared them? Okay, right, because if we just sum them up, they're going to sum to 0. That's how means work, okay? So we would square them, we would get a deviation, we get a squared deviation, and then we would sum the squared deviations. That was our SS, our sum of squares. Who remembers doing all of that? We're going to do something conceptually similar to that. We're going to find a deviation, but this is a non-parametric test. A parametric test is based on a mean. A chi-square is non-parametric, it's not based on a mean. So we're going to find some kind of a deviation, and we're going to square that deviation, and then we're going to sum those squared deviations just like we did. Conceptually very similar. You might notice here the handiwork of Carl Pearson. He's the one who did a lot of this early work, and he was doing it for qualitative variables and also for quantitative variables. Okay, so let's see if we can get this kind of an equation going. We're going to get an observed value, O, minus the expected value, E. Okay? So just like Melanie said a moment ago, we had score minus mean. Here we're doing observed minus expected. We're finding that difference. That could be either positive or negative. We don't really want those to cancel each other out, so we're going to square them just like we did the last time. So I'm going to raise that into the second power. Sorry, that's so faint. It's O minus E squared raised to the second power. And then what we'll do is we'll take that quantity and we will so-called normalize it, which is divided by some kind of value, maybe the expected value. So O minus E squared over E, that's going to be our formula. And you kind of see that here. Now, I'm using slightly different notation, but they have the frequency of the observed, that's F of O, minus the frequency of the expected. Okay, that quantity is in your numerator, it gets squared. And then we're going to normalize that by some kind of expected value. Who's following that? If we do have this on your next computer quiz, I will hand you this and that. Okay, so I won't expect you to memorize this. But I would like you to develop some intuitions about what's going on. Whenever you're in SPSS and you click on chi-square, okay, the number magically comes out. Where does that number come from? It's conceptually similar to what we did earlier with our scores, deviates, square deviates, sums of square deviates. Okay, so let's see if we can go ahead and build these squared deviations that are normalized. Okay, so over here, I'm going to say equals, and I'm going to try to now use this formula for each of our 4 categories. Let's start just with the time category. The observed was 30, minus the expected is 20, so I'm clicking on that. And then I can put a parenthesis around that. I want to take that quantity and square it, because I don't really care about the direction of the difference for the moment. Okay? And then I'm going to divide that by the expected value. Okay? See if that works? And I came up with a 5. I should not have clicked on enter, because then you can't see. Maybe you could see way up top there. It's C9 minus C11, that quantity squared divided by C11. I get a 5. Can I get an amen on the 5? Yeah? All right? All right, so people have that. And you can see that we have a certain spatial relationship. It's the upstairs neighbor minus the middle neighbor. That whole thing gets differenced and squared, and then we divide by that. So I think we can now drag that guy on over. Okay, I think the spatial relationships are right. And I wind up with a 5, a 5, 0.2, and 0.2. Who's okay with all of that? Okay. So now what we have is some observed values, some expected values, which in fact reflect a particular kind of null hypothesis. The null hypothesis was equal likelihood. These are all equally likely. The observations would be 20. The expected values would be 20 in all cases. Okay. We're finding the extent to which we're deviating from that. We're squaring it, and in just a moment we're going to sum those up. Okay? So now we have our square deviates. Okay. And the chi-square test, the chi-square statistic, really is that quantity that we just computed, and then there's a summation sign. So we have to sum up all those square deviates for each of the cells that we have. Okay, so I'm going to say here that this is just the chi-square, and you can say the chi-square stat if you want, but I'll call it just the chi-square. It's just the sum of all of those square deviates, as you can see in the formula. So this is equal to the sum of here are my square deviates. And you know what? I'm even going to label it over here, square deviate, just so you get an idea. I'll put it that way, square deviate. Okay. And now I've summed up all my square deviates, and I come up with a 10.4. We'll see who can corroborate that number. Okay. And we'll see if I lost anybody. Are we okay? All right, so we're doing pretty well there. So that all looks pretty familiar. Who's done something like that in Psych 200? Right? Who's not sure they did something like that in Psych 200? Okay. All right, so maybe many of us learned something new. What we now need to do is we've got this 10.4. We need to put it into some kind of a context. Okay? And the context I'd like to share with you this morning is this frequency distribution. Can you remind me, is this guy positively or negatively skewed? It's been a little while. Yell it out. Is this positive or negative skew? The tail goes off to which side? The right side, the positive side of that really, really long axis, that number line. So this can be a positive skew distribution. Generally, the chi-square statistic generates a distribution just like this. Okay. So what happens is, because we wind up getting different scores and then squaring them, and because in almost all psychological stats we work in the so-called real number system and not the imaginary number system. Who remembers that little ditty from high school, with the imaginary number system or the real number system? Okay, we work with the real number system, so we don't have that imaginary I. So once we start squaring things, if we had zeros and we were squaring them, we could wind up with 0. If we have something that's either negative or positive and we wind up squaring it, we're going to wind up something on the some number that's on the positive side of 0. So what happens is, in the chi-square distribution, you can imagine that if the observed and expected frequencies are pretty similar to each other, you're going to wind up with really, really small square deviations. And when we start summing those up, you're going to make your way just about this far or about this far. You're not going to make your way too far along this axis. Okay? But if you get a big, big difference between the observed and expected values, and you start squaring all those, they really start to accumulate, and you wind up with a really large chi-square value. Okay? And if it's large enough to be some kind of a critical value that you might remember from Psych 200, then we say we can reject the null hypothesis. Okay? So hopefully, those words in the population, the 4 reasons for selecting courses are equally likely. That's our null hypothesis shown here. We're going to compare the observed to the expected. We'll get some measure of the extent to which the observed and expected are lining up with each other. And we can quantify that by saying, well, if they lined up perfectly, we would have absolutely no deviations. If we'd be down here, we'd be nowhere near rejecting the null hypothesis, which is calling for equal likelihood. Okay? On the other hand, if we start departing significantly from that, this is going to grow and grow and grow. We might actually beat some critical value, and we can reject the null hypothesis. Okay? So let me pause there. How many people are following that? Did I lose anybody on that? That's a fair amount. Okay? All right. All right, really good. So now what we need to do is figure out what the critical value is. Anybody recall some of the things we need to take into account when we're trying to figure out the critical value? We know that our observed value of chi-square is 10.4. What's the critical value? How would we go about finding that? I think people remember using a critical value, and some number that you have to beat in order to reject the null hypothesis. Okay? All right, remember doing that. Yeah, do you know how we go? There's a chart, okay? And I usually hand out a chart, but I'm going to try to get away from handing out paper and going in favor of trying to do this online. So what I will show you is, you could have put this in Google, but I'll put it in Google in just before you came in today. I put in something like chi-square critical values, okay? And there are a bazillion of these. You can see the chi-square distribution is up here, okay? And what we'll need to know is our degrees of freedom. We'll come back to that in a moment. And we might go with something like a 5% alpha level, which is, if we flip that around, the 95% value is shown over here. Right? So it's going to be something like 7.81 is our critical value. But before we get too far ahead of ourselves, let's remind ourselves about the degrees of freedom. So according to this sheet, right, how would we figure out the degrees of freedom? I'll prompt you with this. Yell out the degrees of freedom if you think you know it. So here's a formula. Degrees of freedom equals C minus 1. We can think of this. One of the ways of thinking about it crudely is we always create these matrices, and we have basically 4 levels of this variable. We have 4 columns. Okay, so we have 4 columns because we have 4 categories. Okay, and if we subtract 1, then we have 3. So we're going to wind up with 3 degrees of freedom. Who's following that? Okay? So we have 3 degrees of freedom here. So going back to this chart that Jake correctly told us we needed to be at, we can use any one of these values. We'll use the one value that's associated with the 0.05 alpha level. That's correspondingly this number, probability less than the critical value. Here's 0.95. So we need to be able to beat 7.85. Okay, so I'm going to go back over to here, and I'll say something like the critical value df3. You know what, I'll even do it this way. I'll just put here the df is equal to, and that was 4 minus 1, and then I'll say critical value, something like df equals 3, and it was something like 7.81 from that chart. Okay? How many people are following that? So in this particular case, what I can do is I can fill this thing in. And given that I have 3 degrees of freedom, because I have 4 columns, what this is telling me is that I need to derive a critical, an observed value of chi-square that exceeds 7.81. That would put me into this region of rejection, and I could reject the null hypothesis in that case. Okay? All right, who's all right with all of that? So far, so good? Okay, let's learn a new trick. Let's learn a new Excel trick, because it won't always be the case that you can readily get out to the internet. So does anybody happen to know the command inside of Excel for deriving the critical value of any degrees of freedom? If we're doing a chi-square test, does anybody happen to know that? Okay, let's learn a new one. Okay. I'll ask you to do it with me. We'll drop down just 1, and we'll say the same thing. Critical value, degrees of freedom equals 3, and this, of course, is the chi-square critical value. So can you join me by putting in equals? Okay, and we're going to do chi, chi, and then the word or the phrase inv as an inverse. So we have 2 consecutive i's there. Chi, inv, and we open up a left paren, and you get prompted in this way. We're going to do the inverse chi-square distribution. Okay, equals chi in. Who's got that? Okay, lose anybody there? Okay, our probability here, this is actually the tested alpha level, or the criterion alpha level. We're going to put in here 0.05. Okay? We could have put in a different number. It might be that you want to be more stringent and test at 0.01, but we're going to put in 0.05. And how many degrees of freedom do we have? Really loud, everyone? We have 3 degrees of freedom. Okay? And what you'll notice is I get essentially the same number, but I get it to many, many digits of precision. Okay, so if I have 3 degrees of freedom and I want to test at the 0.05 alpha level, I can basically recreate the 7.81 that we had pulled manually from this guy. Right? But we're going to try to get away from that. I'm going to try to not to hand out paper and not use this. We can just have Excel do all the work right for us. Okay? And if you were to change this from 3 to 4, you would get a slightly different critical value. If you change the critical, the alpha level from 0.05 to 0.01, you get a slightly different value. But there it is, 7.81. Okay? All right, who's all right with that? So, show of hands. How many people think we should reject the null hypothesis in this case? How many people think we should not reject the null hypothesis in this case? How How many people are not sure whether we reject the null hypothesis? Is that not sure? Okay, thank you for being not sure. Some people said we want to reject. For those of you who said we do want to reject, I think you're correct. Can you tell us what your reasoning was? Thank you, Jake. Yeah.
The value we calculated chi-square is 10.4.
Right.
It's just a larger value than the critical value.
Excellent. Okay, so we exceeded the critical value, right? And so one way of thinking about that is we always start here, and we have to go this far for our first down. Okay, right? If we can get that far or further, we made it, okay, and we can reject the null hypothesis. And that value is 7.81. You can pull it off of a chart that I could have handed you, or you can find on the internet, or you can use chi-inv, okay? And that's the value we have to beat. Given that we have 3 degrees of freedom, we beat it, we can reject the null hypothesis. Okay? Who's all right with all of that? And can we do a simple variation on that? What I'm going to show you now is a near cousin to the chi-inv command. Okay, it's the chi-dist command. So we're going to be working with the chi distribution, and we're going to call this one the observed alpha level. So it's just a little confusing for students to understand that there are 2 flavors of alpha level. There's actually the criterion alpha level that we adopt as a field, and that's 0.05. Right? Most sciences adopt that one. You can have a stricter one. We typically go for 0.05. And then there's the probability that you actually observe. So if I were to go from here all the way out to here, and I stopped right at that line, 95% of the distribution would be this way, and 5% would be that way. Who's okay with that? Is that working for us? And that's the 0.05 cutoff point. I could have drawn a line a little bit out here and made it the 0.01 value, and that would be 99% that way, 1% that way. And this critical value would have to be slightly larger, right? Because we're going from 0 up to positive infinity, and I'd need a slightly larger value over here. It turns out that we had to get as far as 7.81, and we went that far and then some. We went out to 10.4. So we might ask Excel to tell us, well, given that we're at 10.4, what proportion of the distribution is that way? And what proportion of the distribution is that way? Who's following me? Is that working? Okay. So we know that we typically want to be at 0.05 or further out than that. So we want to see what actually did we observe on our alpha level. The criterion was 0.05. What was our empirically observed alpha level? So I hope you'll do this with me. Equals. We still want to be in the chi-square family, CHI. Right? But now instead of INV, we're going to do basically the same function backwards. We're going to put in the dist function. Okay. And now we have to put in the observed value of chi-square. Can we all yell out the observed value of chi-square for this problem? 10.4? Okay, this is what we observed. Okay. Yeah, okay. And how many degrees of freedom did we have? Real loud? 3? Okay. And I'll leave that there. You can hit the go button. Okay, so here's the chi-dist. We observed that. We got all the way out here. Hey, Excel, what portion of this distribution is to the right of that point? We can hit enter, and we come up with this, 0.015. Okay? So this is the same thing as, I'll put this over here, the sig value inside of SPSS. If we were to do this in SPSS and we were to click on the goodness of fit and we took the even-Steven option, it would have told us 0.015. That would have been the observed p-value. And so Jake and others were correct in rejecting the null hypothesis. We might just sum that up by saying something like this. We reject HO at the 0.05 alpha level. And a couple of ways you can reason that through. You can say because the observed value of chi-square with 3df, and that was 10.4, that's what we observed, exceeds the critical value. That's one way of getting to the rejection of the null hypothesis. We beat the critical value. Another way of getting there would just be we looked at the sig value, we were lower than 0.05, and we all remember our rule. Okay? So you could have done it by looking at the observed alpha level. You could have done it by looking at the critical value. Okay? Those will always give you the same answer. They will use different numbers, but they will come to the same answer as to whether we should retain or reject the null hypothesis. Okay? Who's following all that? Yeah? Okay. How many people had seen sort of that whole cycle? You've seen that whole cycle where you put it into the context of some kind of distribution and you figure out the relative likelihoods and so forth. Yeah, hopefully that looks okay. All right, so that's a simple kind of association, the chi-square. We've done that as a categorical test. Why don't we now do one more example? We'll do it maybe a little bit more quickly. We'll leave that chi-square distribution up there, and we'll now do a chi-square test of independence, okay, which is now going to have us go along 2 dimensions. If you want to save this, you could save it to your assignment inbox, but it's available to you all the time out on the resources folder. And of course, you always get these color-coded answer keys over here. And I encourage you to take advantage of those. And if you ever get stuck, you can just click on it and you see the full genotype in all its glory right there, okay? And then you can go on to a new practice problem, and there's the color-coded answer key. So hopefully you would be well positioned for a computer quiz, and we'll have one in a couple of weeks. Yeah. And that was the chi-square test for goodness of fit. I'm going to put that one away. And then in the same bucket, the same folder out on the S drive, we have its near cousin. We have the chi-square test for independence. Okay. And this one I think is a little bit more conceptually similar to the correlation, which is what we were doing for today. This is a kind of correlation, but it's qualitative. Okay, and why don't I zoom in, because that's really, really small. For our last case, going to a zoom of 200 was pretty effective. Okay, and I'm now on problem 1 in the chi-square test of independence practice set. How many people are there? Did I lose anybody? Yeah, I think the whole gang is there. You doing okay, Shelby? Okay, real good. All right, so now what we're going to do is the same kind of a thing, but we'll run a chi-square test of independence. We'll use, this is our cheat sheet. Again, you won't have to memorize this formula. It might be that after you do a few practice problems, you actually do memorize it, but I will always hand you this. Okay? I've been doing this since, I've been teaching about this since 1993 when I was a TA at Brown during my first year of graduate school. Generally, I don't remember these formulas, but usually after I'm 20 minutes into it, they all come back to me. So I won't expect you to memorize these. So we're going to use the independence formula here. Why don't we just set up our null hypotheses first? So how do we get this going? What's our favorite letter here? H-O. And what's our favorite prepositional phrase? In the population. And then let's take a look at what the problem is. Okay? Give a little bit of context. So here we're going to be looking at the relationship between how people are endorsing or not endorsing affirmative action. Some people are in favor of it. Some people are not in favor of it. You're probably too young to remember during one of the campaigns in the 1990s, there was a big conversation about should we retain or not retain affirmative action. And some people were saying mend it, don't end it. Some people were saying end it, don't mend it. Okay? And then we can see whether those different values on affirmative action, those different attitudes, have some independence or dependence on political party, Republican and Democrat. So we might say something like this. In the population, the, let's see, how will we say it? Attitudes toward affirmative action, that's our first variable. Are, and here's a critical word, independent of political party. Okay, so you can see the two variables that we have going on there. Here's political party, here's attitude toward affirmative action. And those two are independent of each other according to the null hypothesis. Okay? And people have that? Okay. Why don't we go here, and we'll copy that down, and we need to modify this as expediently as we can. That's just what's the fewest number of clicks we can do to change this into the alternate hypothesis. We'll say H1. And all we need to do is insert a not in here somewhere. So attitudes toward affirmative action are not independent of political parties. So now we have a null and alternate hypothesis, and using modus tollens, we can begin to evaluate the null hypothesis about independence. And if we reach some critical value, we can reject the null hypothesis. Okay? Who's all right with all of that? Okay. Questions? So far we're doing okay? All right, now we're on this page. It's a slightly more complicated one because now instead of just saying we can readily compute the expected values, we have to somehow start crossing these one with the next to derive this. Okay, so we have to do a few things in order to get this going. We need to get what we might call row marginals and column marginals, which are essentially row totals and column totals. Okay, so if you'll join me by clicking over here right next to the word Democrat, and we'll get what we will call a row marginal. In fact, a couple of row marginals. So what we want to know here is how many people overall, regardless of party, are voting to mend it, not end it. Okay, so we'll say equals sum. And we'll highlight over these. And I come up with 40. Who can confirm that number? 10 plus 30 is 40. We can probably copy that on down and paste that right into here. And I'm winding up with 60. Okay. So we have row marginals. Of course, we're developing a matrix, so we also have to get column marginals. Okay, so I'm going to go down. It might be advantageous, just to give you a heads up, to go down a row or two. Because in a few minutes, what we're going to have to do is stick right beneath that observed value an expected value. An expected value here, an expected value here, and here. So why don't we give ourselves a little bit of space, come down maybe 2 or 3 rows, it's up to you, but give yourself a little space there, and we'll develop a column marginal. And marginal, again, is our fancy phrase for total. I'm going to center this. You don't have to, but I'm going to center that. Okay, and I'd like to give you a heads up here. We will have a computer quiz. You'll probably have to do one of these. It would be tempting to do something like this. It'd be tempting to click on this guy, auto sum, and or something like that, equals sum, and highlight over all of this. And 10 plus 20 would be 30, okay? That momentarily gives you the correct response, okay? But the warning I'd like to give you this morning is we actually don't want to do that. And the reason is, in just a minute, we're going to insert in here an expected value. And we're going to insert in here an expected value. So we really want to take only the sum of that one, and not any other row or column, not any other cell. Who's following that? That work? Okay. So let's go ahead and build that with an equals sum. We'll click on that one cell that contains the 10. We can put in a comma, and the next cell that contains a 20. Okay, so for me, that turned out to be cells D12 and D15. And then I can hit enter. And then I can put anything I'd like in these intervening cells, and I won't screw up that column marginal. So I've got 30 Republicans in this particular sample. I'm going to now slide that guy on over. Okay, and you can see what I have here. I'm going to turn this one yellow just for a moment. I have a grand total of 100 people. 30 of them Republican, 70 of them Democrat in the sample. I have 40 people voting to mend it, don't end it, and 60 people in the other category, end it, don't mend it. Who's all right with all of that? All right. Now, we have observed values. Because this is a chi-square, what will we need to get after the observed values? Expected values, okay? And we have a formula very similar to what we have on the other side, but now it's this formula. It's a little bit more complicated. It might look like it's just a little more challenging. Why don't we see if we can get these values here? Okay, so how does this go? I'm going to try to get a expected value for that particular cell. Okay, and let's see if we can follow that formula. This will be equal to this. Oops, expected. Let me go back over here. Sorry, equals. Okay, and you can see the expected frequency down on the bottom. Okay, is going to be equal to the row marginal for that cell. So it's going to be equal to 40 times that same cell's column marginal. So I can click on the 30. I went to that one times that one. And I divide by, you tell me. And we're looking at this formula. Sorry, there's a lot of formulas here. We're looking at that formula down toward the bottom of that page. Divide by 100. Okay. And I wind up with a 12. And I'm going to highlight that so you can all see what I'm doing, and we'll see if we're all following where that number came from. Okay. So I needed to somehow figure out, well, how many do I have it mend it, don't end it? How many do I have in Republican, and what would the expected value be after I normalize by that? Okay. Who's got that? Did I lose anybody there? Okay. Let's do that 3 more times, okay, because we have 3 more cells in our 2x2. Right, we have a 2x2 chi-square test of independence. Same kind of an idea, but we're going to use slightly different row and column marginals. So equals this one times the corresponding column marginal, as always normalized by the grand total, and I wind up with 28. Okay, that's an expected value also. I'm going to take my expected values and I'm going to make them look a little bit different. I'll just italicize them so they might stand out a bit for you. Okay, 28. Okay, then I'm going to repeat that exercise for the next row down, and I'll take my 60 times the corresponding column value, which was 30, divided by 100. Okay, I wind up with 18. I'll make that bright yellow, and I'll italicize that. We'll do it one more time. 60 times 70 divided by 100. Okay, and I wind up with 42. And I'll italicize that. I'll let you catch up with me. So it was a lot easier in the world of the chi-square test of goodness of fit, especially when it was an even-Steven model. We had a nice round number like 80. We could divide it by 4. Okay. The expected values kind of popped right out at us. Now we have to do the row marginal by the column marginal, normalized by the total, and that gives us some kind of expected value. Right? So Gabby was right. We'll always need to compare the observed to the expected. Now we have a full-fledged list of expected values. How many people have those? I lose anybody there? Looks like we're all good. Okay, so why don't we go ahead now and we'll get our squared deviates. Call these squared deviates. It's a recurring theme in statistics. We're frequently finding squared deviates. And you might remember what that looked like. That was the observed minus the expected. O minus E. That quantity gets squared. And then we're going to try to normalize that quantity by some kind of expected value for that particular cell. Okay. All right, let's see if we get that going here. So I'm going to do that now for this cell, observed minus expected. That's the deviate. I'll square it, and I'll normalize it. Equals this guy minus the expected value for that same cell. That's the squared deviate, and then I also want to normalize that by the expected value. Oops, excuse me, by the expected value, not by the total. And I wind up with a 0.33 squared deviation after normalization. How many people get that? And I'm going to pause because not everybody's there. That's all right. Yeah. Can I help anybody out with that? Okay, that was observed minus expected, so 10 minus 12, that quantity gets squared, and then we divide by the expected value one more time. I think I can get away with pulling that one over, okay, because I'm using the same spatial relationship, this one minus that one, and I wind up with a 0.14 and change. People got that number? Yep, okay. All right, now why don't we go down and do this two more times. Okay, so we have to do equals observed minus expected. That quantity gets squared, and that whole thing gets normalized by the expected value again for that cell. And I wind up with 0.2 and some change. Okay, and I drag that over, and I wind up with a 0.09 and some change. Okay? So just as we had done way back when, here's our list of scores, here are the deviates, here are the square deviates. Okay? Now we have a bunch of square deviates. They also happen to be normalized. Okay? All right, can we now begin to wrap this up? We're going to go with the chi-square, just a few more clicks here. We're most of the way home. Chi-square, and so as you can see in the formula, the chi-square statistic does have that big summation sign next to it. And what we're summing up is the square deviates after they've been normalized. Here they are, square deviates all normalized. We'll say equals the sum. And I'm going to sum up those four. I have a 2 by 2. I should have 4 cells that are carrying these square deviates. I sum up those 4 square deviates, and I came to a 0.79 and some change. Who can confirm that number? Okay. So remember, if that's our chi-square statistic, we start at 0. We have to get out to some critical value. We'll figure that out in a moment. But the critical values, we haven't gotten very far. We're only just slightly away from 0 because we're at 0.79. Okay. The degrees of freedom. Okay. For this particular case, the formula is, and you can see the degrees of freedom formula here, the number of rows that you have minus 1, and we have 2 rows minus 1, that gives us 1, and we have 2 columns. Okay? And so number of rows minus 1 times the number of columns minus 1. Okay? So 1 times 1 is going to give us, okay, we have 1 degree of freedom. I'm going to hard code it like this. It's actually the quantity 2 minus 1 times the quantity 2 minus 1 because we had 2 rows and 2 columns. That adds up to 1. You can put in a 1 there if you want, but genotypically that's what was going on. Okay? All right, why don't we use our new critical value trick? If I want to get the critical value, did anybody remember what that command was? equals the critical value for chi square equals chi in, okay? And we want a 0.05 alpha level. How many degrees of freedom? You can put in a 1, or I'm going to click on the 1 from upstairs, and I would need to get out to 3.84 in order to claim I have statistical significance, but I didn't get that far. I only got out to 0.79. Equivalently, I can do this. I can say observed alpha level, and I can use my chi-dist equals chi-dist. And I'm going to put in my observed chi-square, which is the 0.79 number. Okay. And I can put in the degrees of freedom. And that's my sig value, which is not lower than 0.05. That sig value is greater than 0.05, so I'm going to wind up retaining my null hypothesis. I only got out about this far. 37% of the population is that way, and its complement is this way. Okay. Who follows that? All right. So we're out of time. I'm going to save all of that, but you can do that practice as you like. When we come back in tomorrow, we're going to do some, there will not be a TED Ed for tomorrow. What we're going to do is these kinds of exercises, but instead of running associations that are qualitative, we'll run linear associations. And we'll see what kinds of values we get there. Okay? Thanks for a great session. Enjoy your day. And thank you for your TED Ed responses on the journal article. Those were great, and I think you've helped the next generation of readers of that article develop some vocabulary. So thank you for that.